Imagine standing on a grassland 12,800 years ago. The air is crisp but not unbearable. Mammoths graze in herds across valleys that stretch to the horizon. Giant ground sloths lumber through forests of spruce and pine. Saber-toothed cats prowl the edges of human settlements, keeping everyone alert, keeping everyone careful. Above you, the ice sheets that once covered half the planet are retreating northward. You can hear water everywhere. Rivers swollen with meltwater, lakes forming where glaciers stood just generations before. The world is warming. The long nightmare of the Ice Age is finally ending. For thousands of years, Earth had been thawing. Slowly, steadily, predictably. Human populations were expanding into territories that had been locked under ice for millennia. People were developing new technologies, building more permanent settlements, creating art and tools that showed increasing sophistication. In the Levant, communities were experimenting with agriculture. In North America, the Clovis people were spreading across the continent, hunting megafauna with elegant stone points. Life was getting easier. The future looked promising, and then everything stopped. Global temperatures plummeted, not over centuries, not even over decades. In some regions, the shift happened so rapidly that scientists struggle to explain it with conventional climate models. The glaciers that had been steadily retreating suddenly surged forward again. Ice sheets that were supposed to be dying began to grow, and this wasn't a minor temperature dip. We're talking about a drop of up to 27 degrees Fahrenheit in some areas. In geological terms, it happened overnight. This period is called the Younger Dryas, and it's one of the most puzzling climate events in Earth's recent history. For over 1,000 years, the planet was thrust back into Ice Age conditions right when it should have been warming. And here's what keeps scientists awake at night. Nobody can agree on why it happened. Was it a massive flood of meltwater that shut down ocean currents? A comet impact that sent debris into the atmosphere? Volcanic eruptions on a scale we can barely imagine? Or something else entirely, something we haven't even considered yet? The evidence points in multiple directions. The theories range from solid to speculative to downright controversial. What we know for certain is that the Younger Dryas changed everything. Civilizations that were flourishing suddenly collapsed. Animals that had survived for millions of years went extinct. And humans, resilient as always, had to adapt or die. If you're finding this fascinating and want to go even deeper into prehistoric mysteries, we've created a book exploring ancient secrets that you can find at sleepytimehistory.com. It's perfect for curious minds who love history. Tonight, we're going to explore what might be the greatest climate mystery in human history. We'll look at the evidence frozen in ice cores, buried in sediment, and written in the rocks. We'll examine the theories, from the accepted to the fringe, and we'll try to understand how a world on the brink of a new age suddenly found itself plunged back into darkness. So get comfortable, because we're going back to the night the world changed. Before we understand what went wrong, we need to understand what was going right. Because 15,000 years ago, Earth was in the middle of what might have been the most hopeful period in recent geological history. The planet was healing. After over 100,000 years of brutal Ice Age conditions, the grip was finally loosening. And it wasn't just loosening slowly. The warming was dramatic, unmistakable, transformative. Picture the world as it existed around 14,700 years ago, right at the beginning of what scientists call the Bulling-Allerud interstadial. That's just a fancy term for a warm period interrupting an ice age, but it doesn't capture the scale of what was happening. Temperatures in some regions had jumped by as much as 15 degrees Fahrenheit in just a few decades. Glaciers that had stood unmoved for millennia were retreating northward at rates of up to a mile per year. You could watch the world transform within a single human lifetime. The ice sheets covering North America and Europe weren't just melting. They were collapsing. Massive chunks the size of small countries would break off and float into warming oceans. The meltwater had to go somewhere, and it went everywhere. Rivers became torrents. Valleys became lakes. Entire new waterways carved themselves across landscapes that had been frozen solid since before modern humans had left Africa. But this wasn't destruction. This was rebirth. As the ice retreated, it revealed land that hadn't seen sunlight in 100,000 years. And life exploded into these new territories with an enthusiasm that's hard to comprehend. Within decades, not centuries, tundra grasslands were spreading across former ice fields. These weren't sparse, struggling ecosystems. These were rich, productive environments that scientists now call the Mammoth Steppe. Grass as far as you could see, thick and nutritious, supporting biomass densities that would make modern savannas jealous. The megafauna thrived in this world. Woolly mammoths moved in herds that numbered in the thousands, following the expanding grasslands northward. Giant ground sloths, some standing 12 feet tall, browsed in forests that were marching steadily across former permafrost. Enormous bison, 25% larger than modern species, grazed alongside wild horses, camels that, yes, camels were native to North America back then, and massive elk with antlers spanning 12 feet across. Predators followed the herds, saber-toothed cats, dire wolves, American lions larger than any cat alive today. The world was full of life, abundant life, successful life. Species that had survived the worst of the Ice Age were now flourishing in the warming climate. Population numbers were exploding, territories were expanding, evolution was in overdrive, with rapid adaptation happening in real time as species colonized new environments. And humans were right there in the middle of it all, adapting faster than anyone. In North America, the Clovis people had developed hunting technologies that were genuinely revolutionary. Their distinctive fluted spear points weren't just sharp. They were engineered, designed with a channel running up the center that made them easier to haft and more aerodynamic when thrown. These weren't crude survival tools. These were precision instruments created by people who understood physics, even if they couldn't write equations about it. The Clovis culture spread from coast to coast in maybe 500 years. That's lightning fast in archaeological terms. They were following the megafauna herds, yes, but they were also following opportunity. The warming climate was opening territories that had been inaccessible for thousands of generations. Fresh water, abundant game, new plant resources. It must have felt like discovering paradise over and over again. Across the ocean, human societies were undergoing their own transformation. In the Levant, the Natufian people were doing something that would change human history forever. They were settling down, not just making seasonal camps, but building permanent structures with stone foundations. Archaeological sites show houses with plastered floors, storage pits for grain, grinding stones for processing wild cereals. These people were on the verge of agriculture, experimenting with cultivating wild grasses that would eventually become wheat and barley. In Europe, communities were emerging from the caves and rock shelters that had protected them during the harshest Ice Age periods. They were building open-air settlements, creating increasingly sophisticated art, developing long-distance trade networks that moved raw materials hundreds of miles. Amber from the Baltic coast was showing up in settlements in central France. Seashells from the Mediterranean were being worked into jewellery in what's now Germany. Forests were expanding rapidly, following the retreating ice sheets northward. Oak, elm and hazel were colonizing landscapes that had been barren tundra just centuries before. These forests supported their own ecosystems, different from the Mammoth Steppe but equally productive. Deer, boar, smaller mammals, birds, fish, in the countless new rivers and lakes. Humans were adapting to these forest environments too, developing new hunting techniques, new tools, new ways of life. The Bulling Alarud was warm enough that tree lines in some regions reached altitudes they wouldn't see again until the medieval warm period. Sea levels were rising steadily as the ice melted, gradually flooding coastal plains and creating new coastlines. But this was gradual enough that people could adapt, could move, could establish new settlements in newly accessible territories. Everything pointed toward continued warming. Every trend suggested the Ice Age was finally truly ending. The climate models that existed in nature's own feedback systems, ocean currents, atmospheric circulation, ice albedo effects, they were all moving in one direction, warmer, wetter, more alive. And then, without warning, the whole system lurched into reverse. The scientists who first discovered it didn't understand what they were looking at. They were studying pollen samples from Scandinavian bogs in the early 20th century, building a timeline of plant life after the last ice age. The sequence made perfect sense at first. As temperatures warmed, you could see Arctic plants being replaced by temperate species. Birch and pine pollen appearing in layers that had once been dominated by tundra vegetation. The progression was clear, orderly, exactly what you'd expect from a world transitioning out of an ice age. Then they hit a layer that shouldn't exist. Right in the middle of the warming sequence, Arctic plants suddenly came back. Not gradually, not as a minor fluctuation, but as a complete reversal. The pollen of Dryas octopetala, a small white flower that only grows in the coldest conditions, reappeared in massive quantities in sediment layers dated to around 12,800 years ago. It was as if someone had rewound the climate by 10,000 years, then pressed play again. They called it the Younger Dryas. Younger because there had been older cold periods during the deglaciation, but none as severe or as bizarre as this one. The name stuck even as scientists realized that this wasn't just a European phenomenon. This was something that had reached across the planet. When ice core analysis became sophisticated enough to measure past temperatures with precision, the true horror of the Younger Dryas revealed itself. Greenland ice cores showed temperature drops of up to 10 degrees Celsius in the North Atlantic region, but it was the speed that made scientists check their data over and over, convinced they'd made a mistake. Some cores suggested the cooling happened in less than a decade, possibly less than 3 years. Maybe, according to some interpretations, within a single year or even a single season. Imagine that. Imagine being a human living through it. Your grandparents' stories about endless ice would have seemed like ancient history. The world had been warming for over 1,000 years. Every generation for 50 generations had seen the ice retreat a little further, the hunting grounds expand, the seasons become a little more forgiving. Then in the space of maybe a decade, possibly less, winter stopped ending. Spring came late, then later, then barely came at all. Summer became a brief interlude between 10-month winters, and it didn't get better the next year or the year after that. The glaciers that had been retreating for over 1,000 years stopped. Then they started growing again. Ice sheets that had been shrinking by miles per decade began advancing southward. In Scotland, glaciers reformed in the highlands. In North America, the ice edge that had been steadily pulling back toward Hudson Bay stopped its retreat and began pushing south again. The Mammoth Steppe, that productive grassland that had supported such abundant life, began transforming back into barren tundra. But the Younger Dryas wasn't just about cold. It was about drought, disruption, and fundamental reorganization of the climate system. In the Middle East, the Natufian settlements that had been experimenting with agriculture faced severe drought conditions. Lakes that had been full and reliable for generations began drying up. The wild cereals they'd been cultivating failed. Some communities simply disappeared from the archaeological record. Others scattered, abandoning their permanent structures to return to nomadic lifestyles. In Asia, monsoon patterns shifted dramatically. Rainfall belts that had sustained human populations for thousands of years moved or weakened. Caves in China show evidence of sudden population collapse. Not gradual decline, but rapid abandonment of sites that had been continuously occupied since before the warming began. South America wasn't spared either. Sediment cores from lakes in the Andes show cooling and increased aridity. Even Antarctica, buried under miles of ice at the bottom of the world, registered the disruption in its ice cores. This wasn't a regional cold snap. This was a planetary climate reorganization happening at a speed that shouldn't be possible. What makes the Younger Dryas particularly maddening for scientists is that it interrupted a clear, well-established trend. Deglaciation wasn't supposed to work this way. When you're coming out of an ice age, the physics are straightforward. More solar radiation reaches the Earth's surface. Ice melts. Albedo decreases as dark ground replaces reflective ice. This creates a feedback loop that should accelerate warming. The system has momentum. It should be very difficult to stop once it gets going. But something did stop it. Something powerful enough to overwhelm all those feedback mechanisms and throw the climate system into reverse. For 1,200 years, roughly 60 human generations, the planet remained locked in near-glacial conditions. Not quite as cold as the worst of the Ice Age, but cold enough to kill. Cold enough to reverse thousands of years of ecological progress. Cold enough to drive species extinct and push human societies to the edge. Then, just as abruptly as it began, it ended. Around 11,600 years ago, temperatures shot back up. The Greenland ice cores show warming that might have been even faster than the initial cooling. Within decades, maybe less, the climate system lurched back toward warmth. The glaciers began their final retreat. The forests started their northward march again. The Younger Dryas was over, but it left scars. In the geological record, in the archaeological evidence, in the extinction patterns of species that didn't survive the cold. It left questions too. Because whatever caused the Younger Dryas wasn't part of the normal climate cycle. It was an interruption, an anomaly, an event that shouldn't have happened but did. and understanding what caused it means figuring out what could be powerful enough to stop a planetary warming trend in its tracks, and then, 1,200 years later, let it resume as if nothing had happened. The ice remembers what happened. Now we just need to learn how to read its memory. The ice remembers everything. Every snowfall that landed on Greenland for the past 120,000 years is still there, compressed into layers like pages in a book written in frozen water. The trick is learning to read it. Picture the process. You fly to the middle of the Greenland ice sheet, to a place where nothing exists except white in every direction. Summer temperatures barely rise above freezing. Winter brings darkness and cold that would kill an unprotected human in minutes. You set up a drilling rig and start boring down through 2 miles of ice. It takes months, sometimes years. You're pulling up cylinders of ice 4 inches wide, section by section, going deeper into the past with every meter. Each year's snowfall creates a visible layer, darker in winter when dust settles on the ice, lighter in summer when cleaner snow accumulates. Near the surface you can count these layers like tree rings. 1 year, 2 years, 50 years. But as you go deeper, the weight of the ice above compresses everything. Layers that were inches thick at the surface become paper thin a mile down. You need microscopes and chemical analysis to distinguish them, but they're still there. Annual records going back beyond the dawn of human civilization, beyond the existence of any written language, into a time when the world was fundamentally different. But the real treasure isn't the ice itself, it's what the ice trapped. As snow falls and compresses into ice, tiny air bubbles get sealed inside. These bubbles are time capsules, containing samples of the atmosphere exactly as it existed when that snow fell. Scientists can extract these bubbles and measure their contents, carbon dioxide levels, methane concentrations, even trace gases that exist in parts per billion. When you drill an ice core from Greenland, you're not just collecting frozen water, you're collecting bottled atmosphere from 12,800 years ago, from 50,000 years ago, from ages when the chemistry of the air was completely different. The Younger Dryas shows up in these cores like a scar. Methane levels plummet right at the boundary layer, dropping by about 30% within decades. This tells scientists something important. Methane comes primarily from wetlands, swamps, areas where organic matter decomposes in waterlogged conditions. When methane levels crash, it means wetlands around the world were drying up or freezing. The planet was getting colder and drier simultaneously. But ice cores reveal something even more precise than gas concentrations. They reveal temperature itself, recorded in the ratio of oxygen isotopes in the ice. Here's how it works. Water molecules come in different weights depending on which isotopes of oxygen and hydrogen they contain. When ocean water evaporates, lighter molecules evaporate more easily than heavier ones. When that water vapor condenses as snow, the heavier isotopes condense first. The ratio between these isotopes in ice depends on how cold it was when the snow fell. Colder temperatures mean more of the heavy isotopes stay in the ocean, so the snow that reaches Greenland is lighter. Scientists can measure these ratios with extraordinary precision, essentially reading past temperatures directly from the chemistry of the ice. The Younger Dryas boundary layer shows isotope ratios shifting dramatically over the course of just a few years' worth of snowfall. Not gradually, not ambiguously. The signal is clear and unmistakable. Something made temperatures plummet faster than should be physically possible given everything scientists understood about climate systems. But ice cores are just one line of evidence. Scientists are careful people. They don't base world-changing conclusions on a single data source, no matter how clear it seems, so they looked elsewhere. Ocean floor sediment cores told the same story from a completely different angle. When you drill into the seafloor, you're sampling millions of years of accumulated sediment. Dead plankton, dust blown from continents, the shells of microscopic organisms that lived in the surface waters and sank when they died. These sediments build up slowly, layer by layer, creating archives that in some places go back to the age of dinosaurs. The Younger Dryas appears in these cores too, but the signal is different. In the North Atlantic, layers dated to the Younger Dryas boundary show dramatic changes in the species composition of foraminifera, tiny shelled organisms that live in the ocean. Cold water species suddenly replace warm water species. The ocean temperature around Greenland dropped by perhaps 5 degrees Celsius. Species that had migrated north with the warming suddenly disappeared, replaced by Arctic forms that hadn't been seen in those waters for thousands of years. Lake sediment cores provided yet another window into the event. When you drill into the bottom of ancient lakes, you find pollen, vast quantities of it, accumulating year after year as trees and plants reproduce. Each plant species produces distinctively shaped pollen, identifiable under a microscope. By counting and identifying pollen grains in sequential layers, scientists can reconstruct what was growing around a lake at any point in the past. It's like reading a botanical history book written in microscopic grains. Lakes across Europe, North America, and Asia all show the same pattern. Right at the 12,800 year mark, forest pollen declines dramatically. Oak, ash, elm, all the temperate species that had been colonizing formerly glaciated regions, they retreat. Their pollen disappears from the record. In their place, tundra plants return. Dryas octopetala, the same small Arctic flower that gave the period its name. Grasses and sedges adapted to cold, harsh conditions. The vegetation was screaming the same message as the ice cores. The world got cold, and it got cold fast. Tree rings confirmed the timeline with year-by-year precision. Ancient wood samples from trees that lived through the transition show dramatic changes in growth patterns. Wide rings indicating good growing conditions suddenly become narrow, compressed, the signature of trees struggling to survive in deteriorating climate. Some ancient bristlecone pines in California show frost damage in rings dated to the Younger Dryas onset, evidence of killing frosts reaching areas where they'd been absent for over 1,000 years. Then there's the black mat. This is where the evidence gets really strange. Across North America, archaeologists kept finding a thin dark layer in sediments, dated to the Younger Dryas boundary, sometimes just a few centimeters thick, sometimes spread across hundreds of square miles. It contains charcoal, suggesting widespread fires. It contains unusual concentrations of iridium and platinum, elements rare in Earth's crust but common in asteroids. It contains microscopic spherules, tiny beads of once molten material, and it contains nanodiamonds, crystals that only form under extreme heat and pressure. Not everyone agrees on what the black mat means. Some scientists think it's evidence of a cosmic impact. Others argue the layer could have formed from wildfires or normal geological processes. But everyone agrees the layer exists, and everyone agrees it dates to the Younger Dryas boundary. The debate isn't about the evidence, it's about interpretation. What's remarkable is how all these different types of evidence converge on the same event. Ice cores, ocean sediments, lake cores, tree rings, archaeological layers, different scientific disciplines using completely different methods, all pointing to the same conclusion. Something happened 12,800 years ago. Something dramatic enough to leave traces in ice and stone and wood and water. Something that changed the world in the space of a human lifetime. The Younger Dryas wasn't a hypothesis or a theory. It was a documented fact, written in layers of evidence stacked hundreds of meters deep across the planet. Scientists weren't debating whether it happened. They were debating why. If the planet really can slam on the brakes that fast, you want to know where the foot pedal is. For many climate scientists, that pedal sits not in the sky or in deep space, but in a vanished lake that once covered the center of North America. Imagine the northern half of the continent at the end of the last ice age. Where you might picture forests and farmland, there is instead a landscape ruled by ice. The Laurentide ice sheet sprawls from what is now the Great Plains to the Atlantic coast, from the Midwest up into the Arctic. In some places it's 2 miles thick. South of this wall of frozen water, everything it melted turned into lakes. One of those lakes was Lake Agassiz. Calling it a lake almost feels disrespectful. This was an inland sea. At its maximum, it covered an area larger than all 5 of today's Great Lakes combined, maybe pushing up toward the size of the Black Sea. It stretched across what is now Manitoba, Ontario, Saskatchewan, North Dakota, Minnesota. Shallow in some places, hundreds of feet deep in others, an immense cold reservoir held in place by ice and low land. The only thing keeping all that water from surging into the oceans was topography and temporary dams of ice and sediment. The Laurentide ice sheet acted like a giant plug. As long as that plug held, Lake Agassiz just kept filling. Glaciers melted, summer temperatures rose, runoff increased. Year after year, meltwater poured into a basin that had no stable, permanent outlet. Now picture that dam failing. This is the core of what's called the meltwater pulse hypothesis. As the Laurentide retreated and thinned, parts of its margin became unstable. Channels formed, tunnels melted through the ice, pressure built behind natural barriers. At some point, the idea goes, a critical threshold was crossed, an ice dam gave way, or a low drainage divide was overtopped, and an unimaginable volume of fresh water burst out in a geologically instantaneous flood. Not a gentle spill, not a river gradually getting bigger. A flood that might have been measured in tens of thousands of cubic kilometres of water, released over decades or even just a few years, enough to raise global sea level by several metres, enough to pour a freshwater lens over the salty surface of the North Atlantic. This is where the story shifts from North American geography to the engine room of the planet's climate. To understand why that matters, you need to think about the oceans not as a static blue backdrop, but as a moving machine. Scientists call one of its key systems the Atlantic Meridional Overturning Circulation. In popular terms, the ocean conveyor belt. Warm, salty water flows northward from the tropics along the surface of the Atlantic. You can feel one of its branches as the Gulf Stream, bringing warm conditions to Western Europe that are surprisingly mild for such high latitudes. As this water travels north, it cools. When water cools, it gets denser. When it gets salty, it gets denser still. Eventually, in the high-latitude North Atlantic, this cold, salty water becomes so dense that it sinks, plunging to the deep ocean and flowing back southward as a cold undercurrent. That sinking is crucial. It's like the pump in a circulation system. It draws warm water north, dumps heat into the atmosphere, then sends cooled water back south to complete the loop. As long as that pump runs, Northern Europe and the North Atlantic region stay much warmer than they otherwise would be. Crops grow where, by latitude alone, you might expect tundra. But the pump has a weakness. It relies on the water being both cold and salty. Dumping an enormous pulse of fresh water into the North Atlantic is like pouring a huge bucket of fresh water into a densely salted soup. You dilute it, you make it lighter. If the surface waters become too fresh, they stop sinking as efficiently. If they stop sinking, the conveyor belt can weaken. In some model simulations, it can collapse entirely for centuries. This is what the Lake Agassiz hypothesis suggests happened at the start of the Younger Dryas. The catastrophic drainage of glacial lakes in North America suddenly flooded the North Atlantic with fresh water. The salty surface was capped by a relatively fresh layer that refused to sink. The overturning circulation faltered. The northward transport of tropical heat was sharply reduced. Take away that oceanic heat delivery, and the climate responds quickly. Europe and the North Atlantic cool first and hardest. Sea ice expands. Snow from winter lingers longer into spring and summer. Brighter, whiter surfaces reflect more sunlight back into space, reinforcing the cooling. Storm tracks shift. Precipitation patterns rearrange. Within a human lifetime or two, regions that had been on a pleasant path out of the Ice Age are shoved back toward glacial conditions. From a physical standpoint, this idea makes sense. It doesn't require unknown forces or exotic physics, just water, gravity, and the known sensitivity of the ocean circulation. Climate models, when you dump large pulses of fresh water into the North Atlantic, reliably produce big regional coolings that look very much like a Younger Dryas analogue. Not identical, but close enough to argue that this is at least a plausible mechanism. There is geological support too. Ancient shorelines and beach ridges across central Canada and the northern United States trace the former levels of Lake Agassiz and its sister lakes. Sediments in river valleys show evidence of enormous outburst floods. Offshore, cores from the North Atlantic contain layers that some researchers interpret as the fingerprints of sudden freshening events. Changes in plankton species, shifts in the chemistry of the water, deposits consistent with iceberg surges and meltwater inputs. Taken together, it paints a tempting picture. A giant lake, an unstable ice dam, a flood into the Atlantic, the ocean conveyor faltering, the world plunging back into cold. But like most stories in paleoclimate, the closer you look, the messier it gets. One complication is the route the floodwaters actually took. Early versions of the hypothesis imagined a dramatic drainage eastward, through the Great Lakes region and out the St. Lawrence River into the North Atlantic. It's a satisfying mental image, a roaring torrent blasting directly into the very part of the ocean that drives the overturning circulation. Later work, though, suggested that at the critical time, the topography and ice configuration might have favoured a different escape route, north and west, along what's now the Mackenzie River system, into the Arctic Ocean rather than the open North Atlantic. If most of the water went that way, it would still reach the Atlantic eventually, but more diffusely spread around the Arctic basin and subpolar seas. That doesn't necessarily kill the idea. Model experiments indicate that large freshwater inputs to the Arctic can also disrupt the overturning circulation as sea ice expands and freshwater spills into the Greenland and Labrador seas. But it complicates the story. It means you're not looking at a single hose pointed straight at the heart of the conveyor belt, but a more distributed, slower-acting influence. Timing is another issue. To make the Younger Dryas story work, the main meltwater pulse has to line up very closely with the onset of cooling. Not centuries apart, but essentially in lockstep. The dam breaks, the flood pours out, the circulation changes, the climate responds. Some reconstructions do show large lake-level drops and big freshwater discharges right around 12,800 years ago. Others place the biggest outbursts a bit earlier or a bit later, or spread over longer periods than the dramatic sudden picture would prefer. There are also questions about magnitude. How much water is actually needed to significantly weaken the AMOC? Models differ. Some suggest truly catastrophic pulses are required. Others say that even more moderate but sustained freshening could do the trick. The geological record hints at multiple meltwater events during the broader deglaciation, not just one. Were they all important? Was one decisive? Or was the system already teetering on the edge, with Lake Agassiz just providing the final push? This is why, in the literature, you often see cautious language. The Lake Agassiz meltwater hypothesis is a leading explanation, not the explanation. It neatly links terrestrial geology, oceanography, and climate. It's grounded in physical mechanisms that can be tested in models. It has supporting evidence on land and at sea. It can explain why the North Atlantic and surrounding regions were hit so hard and so fast. But it doesn't close the case on its own. The drainage pathways are still debated. The precise synchronization between floods and cooling is still being refined. And some aspects of the Younger Dryas, like signals from the southern hemisphere, and the oddities in that black mat layer, don't slide neatly into a simple meltwater narrative. So the Lake Agassiz hypothesis sits in an interesting place. It's the workhorse explanation, the one many scientists start from when thinking about the Younger Dryas. A story of ice, water, and a vulnerable ocean engine. Yet it leaves space, and perhaps even demands space, for additional ingredients. And one of the most controversial candidates for that missing ingredient doesn't come from the oceans or the ice sheets at all, but from above the atmosphere, travelling silently through space. It started, as many scientific arguments do, with an annoyance. By the early 2000s, researchers studying the Younger Dryas kept bumping into details that didn't quite fit the meltwater story. A strange, dark layer of soil and sediment, sometimes just a few centimetres thick, showing up in sites across North America and beyond, all dating to roughly the same moment the cooling began. Charcoal levels spiking, as if vast landscapes had burned. Odd chemical signatures hinting at something out of the ordinary. In 2007, a group led by physicist Richard Firestone suggested a dramatic solution. They proposed that around 12,800 years ago, just as the world was easing out of the Ice Age, Earth was struck, not by one massive object like the dinosaur killer asteroid, but by a fragmented comet or swarm of space debris. The impacts, or airbursts high in the atmosphere, they argued, happened largely over the Laurentide ice sheet and adjacent regions. They called it the Younger Dryas impact hypothesis. In their picture, it goes like this. High above the planet, a comet that has been silently orbiting the Sun for millions of years drifts into a fatal path. As it approaches Earth, tidal and thermal stresses crack it into pieces. Instead of a single crater-forming blow, you get a shotgun pattern of fire from the sky. Some fragments slam directly into the ice. Others explode as airbursts, like the 1908 Tunguska event in Siberia, but on a much larger scale. Each blast releases energy comparable to many nuclear weapons, instantly vaporizing ice and rock, igniting forests, and flinging debris into the upper atmosphere. According to Firestone and his colleagues, the fingerprints of this catastrophe are preserved in a thin boundary layer, what they called the Younger Dryas boundary, found in cores and excavations across multiple continents. In that layer they reported a suite of exotic materials, nanodiamonds, crystals so small they're measured in billionths of a metre. On Earth, they often form under extreme pressures and temperatures, like those produced in powerful impacts. In the boundary layer, researchers claim to find them at concentrations far higher than in the sediments above and below. Magnetic microspherules, tiny glassy metallic beads rich in iron and other metals. These can be created when rock and soil are flash melted and then rapidly cooled, exactly what you might expect from molten droplets flung out of a fiery explosion in the atmosphere or on the ground. High-temperature melt glass, bits of glassy material that appear to have been formed at temperatures well above those reached in normal wildfires or volcanic eruptions. Some samples show signs of having melted and resolidified so quickly that bubbles were frozen in place, like snapshots of rock that had briefly become liquid. Elevated concentrations of iridium and platinum, elements that are more common in meteorites than in Earth's crust. At sites in North America, Europe and the Middle East, some teams reported spikes in these metals right at the Younger Dryas boundary, reminiscent, on a much smaller scale, of the global iridium layer marking the asteroid impact that ended the age of dinosaurs. Put together, Firestone's team argued, these features pointed to a cosmic origin. Too much high energy, high temperature, rare metal chemistry showing up all at once to be a coincidence. If they were right, the implications for climate would be enormous. An impact or series of airbursts over an ice sheet doesn't just scar the surface. It vaporizes ice, melts huge volumes of it almost instantly, and lofts dust, soot, and water vapor high into the atmosphere. Forests and grasslands in the blast zone ignite, feeding continent-scale wildfires. Smoke and ash spread across the northern hemisphere, dimming sunlight, cooling the surface. This is the impact winter idea. Dust and aerosols blocking incoming solar radiation, dropping temperatures even in places untouched by direct blast. For the dinosaur-killing asteroid, this would have been a planet-wide catastrophe. For a smaller, fragmented comet, the effect might be more regional and shorter-lived, but still severe enough to disrupt climate systems that were already delicately balanced. In the Younger Dryas scenario, the impact winter and the ice sheet are linked. Vast amounts of meltwater, suddenly created by the energy released over the Laurentide, would rush toward the ocean. Ice shelves might calve catastrophically. Drainage systems could reorganize in days or weeks, not centuries. In this view, the cosmic event doesn't replace the meltwater hypothesis. It supercharges it. The same floods that could weaken the ocean conveyor belt might be triggered not just by slow warming and unstable ice dams, but by literal explosions in the sky. The climate, already wobbling as the Ice Age ended, receives a series of rapid shocks: fire, darkness, flooding, then a reconfigured ocean circulation. The result, the Younger Dryas plunge into cold. It's a dramatic narrative, and for some, that is both its appeal and its problem. From the very beginning, the Younger Dryas impact hypothesis has been controversial. Some researchers quickly found similar signals: nanodiamonds, microspherules, ropey high-temperature glass, in their own samples from boundary layer sites. Others looked and found nothing unusual at all. Disagreements emerged over methods. How exactly do you identify a nanodiamond under an electron microscope? How do you distinguish a projectile spherule from the products of ordinary fires, volcanoes, or even modern industrial pollution? Could the rare metals be coming from more mundane sources, like volcanic ash or long-distance dust? Might some of the reported anomalies be due to contamination in the lab or misinterpretation of the mineral phases? Underneath the technical arguments lay a deeper tension. Extraordinary claims, like a comet swarm helping to reset the planet's climate, require truly robust evidence. For the dinosaur extinction event, the case rests on multiple independent lines that all converge: a huge globally distributed iridium spike, shocked quartz, tektites, tsunami deposits, and, critically, a single massive crater at just the right age and size, Chicxulub. For the Younger Dryas, the picture has remained fuzzier. Some studies report clear peaks in platinum and other impact-associated materials right at the onset of cooling. Others sample nearby and find no such peaks. Nanodiamond reports are challenged and reanalyzed, with some labs replicating earlier findings and others failing to do so. Over time, the literature has become a patchwork of support, refutation, partial confirmation, and revised interpretations. Then, in 2018, a discovery in Greenland poured new fuel on the debate. Under the edge of the ice sheet, radar surveys revealed a circular depression roughly 31 kilometers across, large enough to count as a true giant among craters. It was named Hiawatha. On maps of Greenland's bedrock, Hiawatha looks disturbingly like the kind of scar an impact would leave beneath an ice sheet. Some of the sediments downstream show hints of impact-related materials. For a moment, it seemed as though the Younger Dryas hypothesis might have found its Chicxulub, a big northern hemisphere crater in roughly the right region. But the key question is timing. Dating a structure buried under more than a kilometre of ice is not straightforward. The first estimates for Hiawatha's age range from perhaps as young as 12,000 years to as old as several million. Subsequent work has tended to push it older, suggesting it may predate the Younger Dryas by hundreds of thousands or even millions of years. If that's right, Hiawatha cannot be the smoking gun for a 12,800-year-old impact. It might represent an earlier, unrelated catastrophe, its imprint preserved under Greenland's ice while the rest of the world's craters eroded away. Or its age might still be refined in the future. For now, it hovers at the edge of the story, intriguing but unresolved. The broader impact hypothesis shares that liminal status. It refuses to go away, too much data hinting at something unusual in that thin boundary layer, but it also refuses to settle into a clear consensus picture. For every paper that strengthens the case for a cosmic trigger, another complicates it, offering terrestrial explanations or questioning the reliability of the signatures. Outside the technical debates, though, the idea has had a powerful cultural resonance. A sudden rain of fire, floods unleashed from collapsing ice, darkness in the sky, cold returning overnight, animals dying, human communities scattered. It's hard not to hear echoes of this in the oldest stories people tell. Flood myths recur in traditions from Mesopotamia to the Americas, from India to the Pacific. Tales of fire serpents in the sky, of stars that fell and burned the world, of a previous age ended by water and cold and darkness. None of these stories on their own prove anything about comets or climate. Oral traditions transform over time, borrow from each other, layer metaphor upon metaphor. Yet there is something haunting about the alignment, a real, geologically sudden return to near-glacial conditions, coupled with evidence, however disputed, of possible fire from the sky at the same moment, and a human memory scape thick with legends of catastrophe at the end of an age. In the end, the Younger Dryas impact hypothesis sits alongside the Lake Agassiz story not as a replacement, but as a possible additional twist. Maybe the climate system was pushed by water alone, maybe it was jolted by ice and ocean, and a coincidental pulse of cosmic debris. Maybe the dark layer marks fires sparked by human hunters, and a drying landscape, not by exploding comets. The evidence is still being sifted, grain by grain, under microscopes and in mass spectrometers. While that work continues, the Younger Dryas remains what it has always been, a puzzle with missing pieces. We can see the sudden drop in temperature, we can trace the rearranged oceans and retreating ice, but the precise combination of triggers, the exact recipe that made the world snap back into cold, remains uncertain. What is clear is that the consequences went far beyond climate graphs and sediment layers. The cooling, reshaped ecosystems ended the reign of some of the largest animals Earth has ever known, and forced human cultures to adapt to a world that had changed almost overnight. To see that fallout, you have to step into a landscape that no longer exists, among animals that now survive only in bones and stories. The first thing you'd notice is the sound. Before the Younger Dryas, late Ice Age North America wasn't quiet tundra and scattered pine. It was loud, wind over grasslands, hooves thundering, tusks cracking ice, the low rumble of herds so large they seemed to pull the horizon along with them. Step into that world in your mind. On the plains, herds of mammoths shuffle and graze, woolly relatives of elephants, their tusks curving like giant ivory scythes. In wetter forests, mastodons move more slowly, browsing on branches and bark, knocking over saplings like they're nothing. Across open country, bands of American horses and camels pick their way between patches of snow and grass. Yes, camels and horses, native to the Americas before they vanished and were later reintroduced by humans. Along river valleys, ground trembles under the weight of giant ground sloths, some as tall as a small house when they rear up, covered in thick fur, claws like scythes hanging from massive forelimbs. In the shadows, predators track them. Saber-toothed cats, with canines longer than your hand, watching and waiting for a weak or unwary target. Packs of dire wolves, heavier and more powerful than modern wolves, closing in on the edges of herds. American lions, short-faced bears, and other carnivores share an uneasy truce at carcasses, testing each other's limits with growls and feints. It wasn't just North America. South America had its own cast of giants, enormous sloths, elephant-like gomphotheres, armoured glyptodonts like living tanks. Eurasia still hosted woolly rhinoceroses, European mammoths, and huge steppe bison. Australia had long since lost its largest animals, but on most other continents, the world of big mammals was still very much alive. Then, over a geologically brief moment, that sound began to fade. By the end of the Younger Dryas, North America's megafauna had been gutted. Roughly 35 genera, entire categories of large mammals, disappeared. Not just a few species here and there, but whole branches of the ecological family tree. Mammoths, mastodons, giant ground sloths, American lions, short-faced bears, saber-toothed cats, the native horses and camels, the massive beavers and armadillo-like glyptodonts, gone. South America lost many of its giants as well. Europe and Asia saw fewer total extinctions, but still significant ones. Woolly rhinos, straight-tusked elephants, some large deer and bison lineages. Africa, interestingly, kept most of its big animals, though populations shifted and ranges contracted. On paper, those are just names. In the landscape, they were entire ways of life, erased. The timing of this die-off has become one of the central mysteries wrapped around the Younger Dryas. Radiocarbon dates on bones, dung fungi and kill sites paint a suggestive picture. Many of these animals were present and abundant as the last glacial maximum ended. Some show signs of gradual decline as climates warmed and habitats shifted. But the real clustering, the point where disappearance becomes a cliff rather than a slope, lines up eerily with the onset of Younger Dryas cooling around 12,800 years ago. Not all species vanish at exactly the same moment. Some hang on in isolated pockets for centuries or even a millennium. Others may have been stressed already. But when you zoom out, the extinctions form a band in time, bracketing the abrupt climate reversal. That's where the arguments begin. Why did so many large mammals vanish just as the world lurched back into cold? One camp points to climate. Megafauna are often specialists. They evolved under certain conditions, particular mixes of vegetation, snow cover, seasonality. The transition out of the Ice Age was not a smooth ramp. It was a series of sharp steps and wobbles. Forests advanced, retreated and reorganized. Grasslands shifted north. Wetlands dried or flooded. A sudden Younger Dryas cold snap could have fragmented already stressed habitats, breaking migration routes, cutting off winter forage, pushing populations already near their limit over the edge. From this angle, the extinction is the biological echo of a climate whipsaw. Too much change, too fast, for creatures whose life histories are measured in decades. Another camp emphasizes a different newcomer on the scene, us. By the time the Younger Dryas hit, humans had spread across the Americas. One particular archaeological culture, called Clovis after a site in New Mexico, left behind distinctive stone spear points, fluted, elegant, clearly designed to be hafted onto wooden shafts and thrown or thrust with deadly efficiency. These tools show up across vast swathes of North America in a relatively narrow time window. The blitzkrieg, or overkill, hypothesis argues that it wasn't climate that finished off the megafauna, but human hunters. In this picture, small but highly efficient bands of people, armed with advanced projectiles and coordinated strategies, moved into naive ecosystems where large animals had no evolutionary experience with such predators. Hunting pressure, even at modest levels, could have rapidly reduced populations that reproduce slowly, especially animals like mammoths and mastodons, which take many years to mature and have few offspring. Over a few centuries, this line of thought goes, the giants were simply eaten out of existence, but the evidence is messy. We have clear Clovis kill sites with mammoth and mastodon bones pierced or associated with spear points. We have cut marks and butchered remains. At the same time, for many extinct species, like giant ground sloths or some of the carnivores, direct evidence of hunting is sparse or absent. Climate reconstructions show real, sometimes extreme environmental stress. It's difficult to say that one force alone did all the work. So a third, more nuanced view has taken shape, a combination. Climate change alters vegetation, and reduces carrying capacity. Populations shrink and become fragmented. Into this vulnerable system, humans arrive. Even low-level hunting applied to already stressed herds can tip the scales. Disease, perhaps moving along with humans or their dogs, might have played a role too. Under this combined pressure model, Megafauna were living on the edge, and the Younger Dryas may have been the last shove. Now add a possible fourth element. If some version of the impact hypothesis is correct, then fire from the sky becomes part of the story as well. Not necessarily the main cause, but another stressor. Widespread wildfires, sudden habitat loss, polluted water, a curtain of ash over grazing lands. Climate, humans, and maybe cosmic debris, all intersecting in the same narrow window of time. Whatever the exact cocktail of causes, one thing stands out. Just as the megafauna vanish, Clovis culture does too. At the Younger Dryas boundary, those classic fluted points and the broader toolkit associated with them drop out of the archaeological record. They're replaced by a patchwork of regional traditions, Folsom, Dalton and others, with different spearpoint styles, different hunting and perhaps social strategies. This doesn't mean the people disappeared. More likely, it means their world did. If your entire way of life is built around stalking mammoths on open plains, a sudden loss of mammoths is an existential crisis. Hunting strategies must change, territories shift, trade networks and social alliances reorganize. In a sense, the extinction of the giants forced a cultural extinction and rebirth. The end of Clovis and the rise of new groups is the human reflection of a deeper ecological upheaval, and that upheaval didn't stop at the species list. It rewrote the land itself. Large herbivores are ecosystem engineers. Mammoths and bison trample saplings, keeping forests in check and maintaining open grasslands. Ground sloths strip branches and uproot shrubs. Their grazing and browsing patterns shape where grasses can dominate, where trees can take hold, where wetlands expand or contract. Take them away, and the feedback loops change. With fewer large grazers, many regions see forests advancing into former grasslands and shrublands. Denser vegetation means different fire regimes, less frequent, but sometimes more intense when fuels build up. Soil composition shifts as dung input declines, as trampling decreases, as different plants take over. Rivers respond to new patterns of erosion and root stabilization. Birds, insects, and smaller mammals adjust, some thriving in the new mosaic, others fading with the old. Over centuries, what had been a park-like, intermittently grazed landscape becomes thicker, more closed, more familiar to our modern eyes. The ghost work of the giants slowly disappears, and beneath all of this lies a deeper, unsettling question. These animals were not fragile newcomers. Mammoths and their kin had survived multiple glacial cycles. They had ridden out advances and retreats of ice, swings in temperature and rainfall, changing coastlines and shifting vegetation for hundreds of thousands of years. Something about this transition was different. Was it simply the speed of the changes at the end of the last ice age? Was it the added pressure of a new kind of predator, one that could coordinate, plan and wield stone-tipped weapons from a distance? Was it, as some suggest, a rare and unlucky convergence of climate stress, human expansion, and perhaps even extraterrestrial disturbance? We don't yet have a final answer. The bones tell part of the story, the sediments another, the stone tools a third. Piecing them together is like reconstructing a vanished symphony from a handful of notes. What we can say is that when the Younger Dryas began, North America still echoed with mammoth footsteps and saber-tooth roars. When it ended, those sounds were gone, replaced by quieter forests and smaller animals, and by human societies feeling their way through a world where the old giants were now only memories. Those memories, and the shock of that loss, would shape the next chapter. How the surviving humans adapted, experimented, and in a few places began building the first monumental structures of the post-megafauna world. When the big animals went quiet, the humans didn't. They couldn't. Silence for them would have meant extinction. On the North American plains, the people we call Clovis had once lived in a world tuned to mammoth rhythms. Their tools, their stories, their migrations, their social bonds, everything was wrapped around following herds, predicting their movements, turning ivory and bone and hide into shelter, clothing and status. Then, right at the Younger Dryas boundary, the mammoths thin out, then vanish. And almost in lockstep, so do the classic Clovis artifacts. Archaeologists noticed this as a sharp break in the soil. Below a certain layer, fluted points, long-distance trade in high-quality stone, big game kill sites. Above it, different shapes, different hunting strategies, different sites. Not a single unified culture blanketing half a continent, but a patchwork quilt. Folsom here, Dalton there, a dozen local traditions adapted to smaller prey and more varied environments. It doesn't look like conquest. It looks like improvisation. If your grandparents grew up in a world where a single mammoth could feed a band for weeks, and you come of age in a world of deer, rabbits, and fish, you're not just learning new skills, you're living in a different mental universe. The prestige of the mammoth hunter gives way to something else. The tracker of swift antelope, the expert trapper, the person who knows which plants can be eaten when the snow stays too long. Clovis, then, is less a vanished people than a molted skin. The Younger Dryas pulls away the old ecological scaffolding, and human cultures on the continent reconfigure themselves to fit a quieter, more fragmented landscape. Across the ocean, in the hills and valleys of the eastern Mediterranean, another experiment in human living is underway when the cold returns. The Natufians in what is now Israel, Jordan, Lebanon, and Syria are some of the first people we know of who seem to have tried something like settled life before farming. Before the Younger Dryas, they cluster in stone-built hamlets, some occupied for generations. They harvest wild cereals, ancestors of wheat and barley, that grow thick on the hillsides as the climate briefly softens near the end of the Ice Age. From a distance, it looks almost like a preview of village life. Semi-permanent houses, cemeteries, tools specialized for grinding seeds and processing plants. Not quite farmers, not quite nomads. A middle path, resting on a comfortable assumption. The wild grain will be there again next year. Then the Younger Dryas arrives, and the Levant's climate flicks back toward arid. Rainfall declines. The stands of wild cereals that once grew thick and predictable become patchy, unreliable. In some regions, woodland and grassland retreat. In others, drought bites hard. For foragers who have anchored themselves to particular spots on the land, this is a crisis that cuts to the bone. One response would have been to abandon the experiment and return to a fully mobile life, tracking whatever resources remain. Some groups likely did exactly that. But in the archaeology of later Natufian sites, you can see another path emerging. Grain becomes more central. Grinding stones multiply. The charred remains of plant seeds shift subtly from mixtures of many wild types to more focused sets, dominated by the ancestors of domesticated crops. Over centuries, plant remains start to show physical changes, thicker seed coats, non-shattering stalks that hint at human selection. Fields that once belonged completely to the wind and the birds are being nudged, season by season, into something else. It may be that the Younger Dryas, by making wild resources less dependable, pushed the Natufians into a strange new bargain with plants. If you protect us from random failure, we'll protect you from random death. We'll weed for you, water you when we can, save your best seeds and put them back into the ground. Agriculture in this telling isn't a triumphant invention. It's a negotiated truce with uncertainty. Move a bit north and east, onto the limestone plateau of southeastern Turkey, and another kind of response to crisis rises out of the rock. Göbekli Tepe does not look like something you build when times are easy. Around 11,600 years ago, right at the transition out of the Younger Dryas as temperatures spike and glaciers retreat for good, people in this region begin carving and raising enormous T-shaped stone pillars, some weighing more than 50 tons. They set them in circles and ovals, arrange them with care, and decorate them with animals. Foxes, boars, snakes, birds, abstract symbols whose meanings we can only guess. These are not the works of a settled, city-building civilization. As far as we can tell, the people who gathered here were still hunter-gatherers, perhaps early experimenters with cultivation, but without permanent urban centres, writing, or metal. Yet they invest staggering amounts of labour in a place that appears to have been a ritual centre, perhaps visited seasonally, perhaps for feasts, initiations, or ceremonies tied to the turning of years. Why then? Why there? No one knows for sure. But the timing is uncanny. The oldest levels of Göbekli Tepe fall just after the Younger Dryas's end, a few centuries after generations had endured droughts, abrupt cold, and shifting resources. Some researchers see the site as a monument to survival, a stone testament built by people whose grandparents grew up in a harsher world and watched it suddenly, disorientingly, thaw. Others suggest it could be a response to instability itself, a way to bind scattered groups together in shared myth and ritual, to coordinate labour and exchange in a world where climate had recently shown itself to be unpredictable and dangerous. When nature stops feeling reliable, you might start trying to anchor meaning in objects that will outlast you. Pillars sunk into bedrock, stories etched into stone. Whether it was mourning, thanksgiving, or a bid for control, Göbekli Tepe marks a turning point. Shortly after its construction, the broader region sees a rapid spread of agriculture and eventually true village life. It is as if the people who gathered there were standing at the hinge between worlds. Behind them, hundreds of thousands of years of mobile foraging. Ahead of them, fields, walls, and everything that follows. Some scholars have begun to see the Younger Dryas itself as the catalyst for this hinge. Before the cold snap, the late Ice Age offered pockets of relative abundance, rich foraging grounds, predictable seasons, big herds. In such places, the cost of staying mobile and flexible was low, and the benefits of settling and betting everything on a few crops were dubious. The Younger Dryas changes the calculus. Now in some regions, the old way becomes precarious. Wild plants fail more often, animal migrations become erratic, water sources dry, then flood, then dry again. Under those conditions, the risk of trying to control a small patch of land, clearing, planting, storing, begins to look less insane. Fixed fields and granaries become paradoxically a hedge against a wildly swinging world. Across Eurasia and the Near East, the archaeological record after the Younger Dryas shows a cascade of changes. More permanent houses, storage pits, domesticated plants and animals, pottery, eventually the first true towns. It is messy, regionally varied, full of false starts and local traditions, but running through it is a common thread. People trying to pin down at least one part of their environment. Elsewhere, the Younger Dryas leaves different fingerprints, but the pattern of disruption and adaptation repeats. In parts of East Asia, abrupt cooling and drying alter the monsoon systems, reshaping river flows and floodplains. Hunter-gatherer groups along what would become the Yellow and Yangtze river valleys face shifting fish runs and plant communities. Over the following millennia, these regions too give rise to early forms of agriculture, millet and rice, perhaps seeded by foragers who had learned, in hard years, to tend the most reliable patches of edible plants. In Africa, the story is patchier, but climate records show that the so-called Green Sahara, with its lakes and grasslands, flickers back toward aridity during the Younger Dryas before greening again. Populations following fish, hippos and antelope along ancient rivers may have been forced to compress into refuges or move with shrinking wetlands. These pressures echo later in the pastoral and agricultural revolutions that sweep across the continent as conditions stabilize. In South America, glacier records from the Andes and pollen from lake sediments record their own version of the snapback. Highland and lowland groups alike must have adjusted hunting grounds, planting cycles, and travel routes as temperatures and rainfall patterns shifted. The great agricultural societies of the Andes and Amazon would flower much later, but they grow in soils whose human memory includes abrupt climate lurches, and in cultures already skilled at engineering terraces, canals and raised fields to buffer against them. In all these places the details differ. Some groups move more, some build granaries, some turn to herding, others to fishing, others to ritual. Some vanish from the record entirely, leaving only scattered tools and the faint signatures of cooking fires in the soil. Yet a single impression emerges when you zoom out. The Younger Dryas is not just a story of ice cores and pollen diagrams. It is a story of human minds under pressure, of bands and villages forced to reinvent what it meant to make a living, to remember the past, to imagine the future. Out of that pressure cooker come some of the defining features of our world: farming, permanent architecture, long-distance trade, shared ritual centres, social hierarchies complex enough to organise the quarrying and hauling of megaliths. We're used to thinking of civilization as the product of stability: gentle climates, reliable rivers, fertile soils. The Younger Dryas suggests a different possibility, that our deepest civilizational habits were forged not in comfort, but in crisis. Human beings survived the cold shock. More than that, they adapted, and in adapting they changed their relationship to the planet itself. A world of wanderers began, hesitantly at first, to become a world of builders. But just as new villages and stone circles were rising, the climate was about to throw one more surprise: The same abruptness with which the Younger Dryas began would mark its end, and with that final shift the stage was set for the full unfolding of the Neolithic age. When you start asking why the Younger Dryas happened in the first place, the answers very quickly stop feeling solid. We've already walked past the big suspects, the great meltwater floods pouring off the North American ice sheet, perhaps jamming the Atlantic conveyor belt. Maybe a comet or asteroid breaking up in the atmosphere, setting off fires and dust clouds. Each of those ideas has evidence in its corner, and problems nipping at its heels. But they're not the only players on the board. There is, for instance, the quiet suspicion that somewhere in all of this, a volcano went off at exactly the wrong time. About 12,900 years ago, right on the doorstep of the Younger Dryas, an explosive eruption tore open the ground in what is now Western Germany. Today we call it the Lake Agassiz eruption, named after the lake that fills its crater. At the time, it would have been an almost incomprehensible spectacle. Columns of ash punching into the stratosphere, pyroclastic flows racing down valleys, forests flattened under blankets of pumice. Volcanoes like this don't just blacken the local sky. They pump sulfur into the upper atmosphere, where it forms tiny droplets, sulfate aerosols, that can hang for years, scattering sunlight back into space. After big eruptions in recorded history like Tambora in 1815, the following years are sometimes called years without a summer. Crops fail, snow lingers, the world feels slightly dimmer. So it's tempting to look at Lake Agassiz and imagine a similar script, only bigger, longer, more consequential. Ash from that eruption is found across large parts of Europe. The timing is close to the Younger Dryas onset. A veil of volcanic aerosols could, in principle, have been the first nudge that tipped an already fragile climate toward a deeper, longer cold phase. But close is not exact. The eruption seems to precede the sharp temperature drop by enough time that some researchers see it as merely a prelude, not the main act, and the atmospheric effects of even a large eruption usually last a few years to a decade, not 1,200 years. That hasn't stopped volcanism from lingering in the background of the debate. Lake Agassiz may not have single-handedly frozen the North Atlantic, but it might have helped weaken the system. A couple of years of dimmed sunlight could have grown snowpacks, cooled seas, encouraged sea ice to spread. In a climate system already primed by ice sheet melt and changing ocean currents, that might have been enough to push it over one of those invisible edges we call tipping points. Volcanoes are only one kind of wild card. Another lies much farther away, 150 million kilometers out, in the shifting moods of the sun itself. Our star is not a perfectly steady lamp. Its output wobbles over time, in cycles of about 11 years and longer, waxing and waning in concert with sunspots, magnetic storms and deeper processes we still don't fully grasp. These changes are small, fractions of a percent, but when you spread them across an entire planet for centuries, the cumulative effect can matter. In the Greenland ice, scientists measure the concentration of a rare isotope called beryllium-10. It's born high in the atmosphere when cosmic rays, high-energy particles from space, slam into air molecules. When the sun is active and its magnetic field strong, fewer cosmic rays reach Earth, and beryllium-10 production drops. When the sun is quiet, the opposite happens. If you read those tiny atoms like a diary, parts of the Younger Dryas look suspiciously like a time when the sun went into one of its quieter moods. Beryllium-10 levels are higher. Cosmic rays, less shielded by solar activity, were making more of it. That suggests solar output may have dipped at just the wrong moment. A slightly fainter sun doesn't sound dramatic, but imagine combining that dimming with fresh, cold meltwater, flooding into the Atlantic, disrupting the conveyor belt that carries heat northward. The surface of the North Atlantic cools, sea ice spreads a little farther each winter, snow lingers into spring, a volcano goes off in Europe, adding a veil of sulfates. The next year begins on a slightly whiter, slightly colder planet. Under those conditions, the climate system doesn't need a huge shove. It just needs one more small, well-timed push, and it may lurch into a new, colder pattern all on its own. This is where the idea of cascading causes becomes hard to avoid. Instead of hunting for one single culprit, a comet, a lake, a volcano, some researchers now picture the Younger Dryas as the end result of a pile-up. A cooling sun, restless ice sheets, a jittery Atlantic overturning circulation, occasional explosive eruptions, Each factor on its own might have produced only modest bumps and dips. Together they might have synchronized into a perfect storm, locking the northern hemisphere into a deep chill. The story becomes even stranger when you look south. In Antarctica and the southern hemisphere, climate records tell a slightly different tale. Around the time the Younger Dryas begins in the north, the south is actually nearing the end of its own cold spell, the Antarctic cold reversal. As the North Atlantic plunges back into glacial-like conditions, parts of the Southern Ocean and Antarctica seem to be stabilizing, even warming slightly. This out-of-step dance has given rise to an idea with an evocative name, the bipolar seesaw. Picture the planet's heat budget as a long, slow trade between hemispheres, mediated by the oceans. When deep water sinks in the North Atlantic, it eventually rises in the Southern Ocean, carrying heat with it. Speed up the conveyor in the north, and you can, over time, cool parts of the south. Slow it down, perhaps by dumping fresh meltwater into it, and the balance shifts. The north cools sharply, while stored heat gradually seeps out in the south. In this view, the Younger Dryas isn't just a northern event, it's part of a global rebalancing act. Cold air locks itself over Greenland and the North Atlantic. Storm tracks shift. Meanwhile, on the other side of the world, the Southern Ocean is quietly exhaling old warmth, nudging Antarctic climates and southern monsoons in directions that don't line up neatly with what's happening up north. Tangled into all of this are the tipping points and feedback loops that make climate such an unnervingly non-linear system. Once cooling begins in the north, ice and snow start to spread. White surfaces reflect far more sunlight than dark ocean or soil. That means less solar energy is absorbed, which leads to more cooling, which grows more ice, which reflects even more light, a classic positive feedback loop. Sea ice pushes further south each winter, making it harder for the ocean to release heat to the atmosphere. Winters deepen. Summers never quite claw their way back to the warmth they once had. Vegetation shifts add yet another layer. Forests stressed by cold and dryness thin out, replaced in some places by open tundra or steppe. Dark canopies that once absorbed light give way to paler, more reflective ground covers. Dust storms from exposed glacially ground sediments add hazy veils to the sky. Each change is small. Together they reinforce the cold. From a distance, the Younger Dryas can look like a simple on-off switch. Warm, then cold, then warm again. Up close, it resembles more a knotted mesh of causes and consequences, every thread tugging at the others. That, in the end, may be why it remains one of the most debated episodes in paleoclimatology. We have drill cores that reach back over 100,000 years, each annual layer of ice or mud a thin, fragile page in Earth's history. We can count trapped bubbles of ancient air, measure isotopes atom by atom, model ocean currents on supercomputers. And yet, when we stand in front of the Younger Dryas, we are still forced to use words like maybe, probably, and it's possible that. Perhaps a burst of meltwater was the key. Perhaps an especially quiet sun helped. Perhaps volcanic ash dimmed the sky at exactly the wrong moment. Perhaps the oceans were already teetering on the edge of a new circulation pattern, and the last straw could have been something we haven't even thought to measure. The uncertainty can feel unsettling, but it is also, in a way, part of the story's power. It reminds us that even with all our instruments and equations, we are still learning how delicately the planet's systems are interlaced, how slight shifts in one corner can ripple into sudden transformations elsewhere. It hints that the world your ancestors walked into 12,800 years ago was shaped not by a single dramatic twist, but by a chorus of smaller voices rising together into a storm. And as abruptly as that storm began, it would, just over a millennium later, subside, just as sharply and just as mysteriously, leaving behind a warmer world and a species increasingly ready to reshape it. If the beginning of the Younger Dryas feels like someone flipped a switch, the end feels like they snapped the breaker. About 11,600 years ago, in the ice high above what is now Greenland, something changed with terrifying speed. In the layers of snow that were falling then, later compacted into ice, you can see it as clearly as if a thermometer had been frozen in place. One year, the isotopes tell us, the air above the ice was brutally cold, Younger Dryas cold. Within what may have been just a few years, possibly even less, temperatures there had jumped by on the order of 10 degrees Celsius. That is not a gentle warming. On human scales, it's like stepping out of late February into late May between one lifetime and the next. On geological scales, it's a lightning strike. In the Greenland ice cores, the transition looks almost like a knife edge. For more than 1,000 years, the layers build up with the signature of a frigid, unstable climate. Heavy isotopes that whisper cold, dust that hints at dry winds and sparse vegetation, trapped bubbles of air holding lower greenhouse gas levels. Then, abruptly, the pattern shifts. The isotope ratios swing toward values that mean warmer temperatures. Dust concentrations drop, suggesting calmer winds and greener landscapes. Methane, linked to wetlands and biological activity, rises. It's as if the ice is telling you, in a few thin layers, that the world outside has stepped into a different state. If you could zoom through those annual bands like pages in a flipbook, the story would feel wrong somehow. Your mind expects slow arcs, not sharp corners. It expects climate to crawl, not leap. But over and over, independent cores, drilled by different teams at different times, show the same pattern. The Younger Dryas doesn't fade out. It stops. What could make an entire climate regime, anchored by ice sheets and ocean currents, give way so quickly? One leading suspect is the same sprawling system that may have helped trigger the cold in the first place. The Atlantic Meridional Overturning Circulation, the great conveyor belt that moves warm surface water northward and returns cold deep water south. In many models, once the flow is weakened by fresh meltwater or other disturbances, it can settle into an alternative mode, a sluggish, cold-favouring pattern. But that state isn't necessarily permanent. As ice sheets shrink, as meltwater pulses slow, as salinity and temperature patterns shift, the system can creep back toward a threshold. Cross that threshold, and the overturning can suddenly strengthen again, hauling heat northward with surprising speed. In that view, the end of the Younger Dryas is the moment the conveyor belt snaps back from its weakened mode to its vigorous one. Warm Atlantic waters surge farther north, sea ice retreats, winters soften, summers strengthen. The North Atlantic region doesn't just warm because the sun climbs slowly higher in its seasonal dance. It warms because an entire planetary heat pump revs back up. But the oceans were not acting alone. While the Younger Dryas played out, Earth was still sliding along its long, slow orbital cycles, the Milankovitch rhythms that subtly alter how sunlight is distributed across the planet. These cycles don't change the total amount of solar energy much, but they do shift when and where it hits most intensely. By about 11,600 years ago, the Northern Hemisphere summer insolation, the strength of sunlight during northern summers, had been rising for some time. That slow orbital nudge had been pushing against the Younger Dryas cold from behind, like a steady hand on the back of a locked door. At some point, the combination of stronger summer sun, shrinking ice sheets, and a gradually changing ocean may have crossed a critical line. Sea ice that once lingered well into spring began to melt a little earlier. Snowpacks retreated a little farther each year. Dark ocean and land surfaces absorbed a bit more heat, amplifying the seasonal warming. Once that warming breached whatever invisible threshold was holding the system in its colder mode, feedbacks that had favoured ice and cold flipped direction. The atmosphere may have joined in as well. During the Younger Dryas, atmospheric carbon dioxide and methane were lower than in the warm periods before and after, but not frozen in place. As southern oceans released stored CO2, as vegetation expanded and wetlands grew in some regions, greenhouse gas levels began to creep upward. Greenhouse gases work slowly, but their influence accumulates. A little more CO2 in the air makes summers just that bit more effective at melting snow and ice. Less ice means more absorbed sunlight, which means more warming, which melts more ice, a feedback loop running in the opposite direction of the one that had helped lock in the Younger Dryas chill. Put all of this together, orbital forcing, ocean circulation, greenhouse gas feedbacks, and you get a picture that is less single cause and more conspiracy of timing. For over a millennium, the system had managed to hold to its cold Younger Dryas pattern, maintained by weakened overturning, widespread ice, reflective landscapes, and whatever lingering solar or volcanic quirks had helped get it there. Then the balance tipped. Slowly at first, imperceptibly, and then from the perspective of the ice, almost all at once. When the dust settled, literally and figuratively, the planet had entered a new chapter. We call it the Holocene. Compared to the wild swings of the preceding glacial cycles, the Holocene is a remarkably calm interlude. Warmer than the Younger Dryas, but not in the furnace of a greenhouse Earth. Cooler than some deep past epochs, but with a climate that, on global scales, has stayed within relatively narrow bounds for more than 10,000 years. This is the climatic cradle in which nearly everything we think of as history unfolds. As the Younger Dryas ended, glaciers retreated farther into the mountains. Sea levels, already rising, continued their slow climb, reshaping coasts and flooding old river valleys into new estuaries and inland seas. Forests advanced northward into areas that had been steppe and tundra. Lakes stabilized. Rivers found more predictable courses. For human communities scattered across Eurasia, Africa and the Americas, that meant something that had been scarce for tens of thousands of years: reliable seasons. In the Near East, where wild grasses had long grown along the edges of wetter patches, people began to notice that seeds scattered near their camps sprouted into more grain the next year. Over generations, that observation became tending. Tending became deliberate planting. Planting, paired with increasingly predictable rainfall and temperature patterns, became agriculture. Elsewhere, in China, in the Americas, in parts of Africa, similar experiments in cultivation and animal management would unfold, each rooted in local species and traditions, all made easier by a climate that no longer careened between extremes on the scale of a human lifetime. Stable growing seasons allowed surplus. Surplus allowed some people to specialize, to make better tools, to carve, to weave, to plan, to record. Villages grew into towns, towns into early cities. Clay tokens evolved into marks on tablets, into writing. From one perspective, all of this depends on a set of familiar inventions: the plough, the kiln, the loom, the alphabet. From another, deeper perspective, it depends on something more basic: a planet whose climate had, for once, decided to stop lurching and start lingering. The Younger Dryas, when seen against the longer backdrop of the Ice Age, looks like a last violent shiver. For roughly the past 2.5 million years, Earth has cycled between long glacial periods and shorter, warm interglacials, driven by those slow orbital changes and amplified by feedbacks in ice, oceans and atmosphere. Temperature has marched up and down by several degrees. Ice sheets have advanced to mid-latitudes and then melted back, again and again. The Younger Dryas sits near the end of that pattern. A final, sharp, cold relapse, just as the planet seemed poised to settle into a warm phase. After it ends, the great northern ice sheets never return in the same way. There are wobbles and regional shifts, but no renewed plunge into full glacial conditions. In that sense, the Holocene is unusual, not unprecedented in all of Earth's vast history, but, in the specific rhythm of this ice age, a notably long, notably steady warm plateau. We live on that plateau. Every field of wheat, every stone city, every ship that crossed a predictable sea has been a beneficiary of that relative calm. It's tempting from the inside to see such stability as normal, as the baseline state of the planet. The Younger Dryas, with its abrupt freezes and equally abrupt thaw, can feel like an exception, a strange excursion from an otherwise orderly record. But the deeper you look into deep time, the more that assumption wobbles. The norm, over millions of years, is change. Slow, fast, gentle, violent, driven by continents drifting, volcanoes breathing, life itself rearranging the air. The Holocene, with its subdued climate swings and hospitable temperatures, may be the exception, a lucky pause in a usually more restless song. Everything we have built so far has been tuned to that pause. If the Younger Dryas teaches anything, it is that Earth's climate is capable of moving between very different states on timescales that matter to individual lives, not just to rock strata. It can lock into a pattern for 1,000 years, and then, in the space between one generation and the next, unlock again. Our entire story, agriculture, writing, cities, history as we tell it by lamplight, unfolds in the aftermath of one of those unlockings. The world that emerged from the Younger Dryas was not just warmer. It was unusually stable, and that stability, as secure as it can feel when you're born into it, is not guaranteed. If this were only an ancient story, it might be comforting. A strange, cold snap, a 1,000-year detour into winter, an abrupt return to warmth. Then, at last, the long, calm Holocene, and us. But the reason the Younger Dryas still pulls at scientists and keeps creeping into modern climate debates is that it doesn't feel entirely finished. It feels, in some ways, like a rehearsal. Because one of the main suspects in that ancient drama, The Atlantic meridional overturning circulation, the great ocean conveyor that helped steer the Younger Dryas into being, is not just a concept in a textbook. It's a living system, still humming beneath the surface of the Atlantic, still carrying heat north, and today it is measurably slowing down. As Greenland's ice melts under modern warming, as Arctic sea ice thins and northern rivers pour more fresh water into the ocean, the surface waters of the North Atlantic are becoming less salty in places, less dense, less eager to sink. All the ingredients that, in models and in paleoclimate records, can weaken the overturning circulation are quietly accumulating again. Nobody is claiming that tomorrow we wake up in another Younger Dryas. The world now is different. The ice sheets are smaller, greenhouse gas levels are far higher, the background state of the climate is warmer, but the physics of density, salt and sinking water haven't changed. Oceanographers are watching the AMO sea like you might watch a sleeping giant whose breathing has become just a bit shallower. The question that hangs over this monitoring is an uncomfortable one. Could the system cross another threshold? Not necessarily into an Ice Age world. That would be very hard with so much CO2 in the air. But into a new pattern of currents, storms, and regional climates that looks nothing like the one we built our cities and farms around. This is where the Younger Dryas steps out of the past and sits down beside us. Hidden in that event is a lesson about tipping points. For a long time, it was easy to imagine Earth's climate as basically gradualist. Temperatures creeped up or down over tens of thousands of years, ice sheets inched forward or retreated, sea levels rose and fell like slow, heavy tides. Changes were real, even dramatic, but they were buffered by long timescales. The Younger Dryas, and other abrupt shifts in the ice cores, show that this picture is incomplete. Complex systems, from ecosystems to financial markets to ocean circulation, can behave in a particular way. For a while, they absorb stress. Push them with fresh water or greenhouse gases or land use change, and they bend, flex, adjust. Then, beyond some hidden point, they don't bend anymore. They flip. In climate science, that hidden point has a name, a tipping point. It doesn't have to be dramatic on the ground. No alarm goes off over the North Atlantic when the overturning circulation reorganizes. No red line appears across the sky when sea ice or monsoon patterns cross some critical threshold. But the system's internal feedbacks quietly switch sign. What once resisted change now amplifies it. The Younger Dryas is one of the clearest real-world examples of such a flip. A vast ocean current, a sprawling ice sheet, atmospheric circulation, and feedbacks in snow and sea ice combine to shove the climate into a different mode, then let it snap back out again. For modern scientists trying to understand what might happen as we load the atmosphere with greenhouse gases, this is not just a curiosity, it is a test. Climate models are the main tools we have to peer into the future. They're built from equations that describe fluid flow, radiation, clouds, chemistry, and ice. They're calibrated against modern measurements. But to really trust them, scientists ask a harder question. Can these models also recreate the wild swings of the past? If a model, when fed the right boundary conditions, ice sheet sizes, orbital settings, greenhouse gas levels, fails to produce anything like the Younger Dryas, that's a red flag. It suggests the model may be missing some crucial feedback, some way that ocean and ice and atmosphere can gang up to produce abrupt change. On the other hand, if a model can realistically simulate the onset and end of the Younger Dryas, match the timing and magnitude of the temperature swings seen in ice cores and sediments, match the patterns of change in different regions, then confidence grows that the same model might be able to handle whatever is coming next. In that sense, those icy layers in Greenland and Antarctica are not just archives, they're exam questions. Given this configuration of the planet, they ask the models, what happens? Some models pass more of those questions than others. None are perfect. But every time the Younger Dryas is successfully captured in a simulation, it tightens the link between deep past and near future. The echoes are not only physical, there is a softer, more human thread that some researchers follow, the idea that memories of Younger Dryas-era catastrophes might still shimmer faintly in our oldest stories. Across cultures scattered around the world there are flood myths, tales of waters rising suddenly, engulfing valleys and lowlands, forcing people into boats or onto mountain refuges. In Mesopotamia, the story of Utnapishtim in the Epic of Gilgamesh. Later, the story of Noah. In Hindu traditions, Manu warned by a fish of a coming deluge. Among many Native American nations, narratives of great floods, shifting rivers, and worlds remade. Most historians treat these as cultural motifs, shaped and reshaped across millennia, not as direct eyewitness reports of a single event. Yet some geologists and mythographers wonder if behind the shared pattern there might be fragments of real experiences. Abrupt sea level jumps as glacial lakes drained, river courses transformed by meltwater floods, coastlines drowned as the last ice retreated. If the Younger Dryas did involve outburst floods, sudden climate flickers and strange skies, it's possible that the communities who lived through its closing chapters carried forward stories of water and loss, of worlds ending and beginning, long after the ice itself had vanished. Whether or not specific myths can be pinned to specific events, the parallel is suggestive. The line between geology and memory is thin in deep time. Human beings are storytelling animals. When the world lurches, we do not only adapt physically, we narrate. We encode shock and survival into tales that last longer than any one village. That brings the Younger Dryas into yet another domain: philosophy. To think about this ancient cold snap is to be reminded again of how contingent our world is. Civilization, with its libraries and satellites and glowing screens, feels solid when you're inside it. Streets look permanent, calendars feel like the bones of time, but everything we recognize as normal depends on a particular slice of climatic luck. 10,000 years of relatively narrow temperature swings, predictable growing seasons, and coastlines that have not marched inland or outward too far, too fast. The Younger Dryas sits right behind that luck like a ghost at the door, whispering that it could have been otherwise. If the AMOC had stayed in its weakened mode a little longer, if the orbital configuration had been slightly different, if the ice sheets had behaved in some other way, perhaps the Holocene would have been shorter, or more jagged, or never quite as stable. The planet does not promise us stability. It simply offers intervals of it, framed by long eras of restlessness. Our species has survived both. But the kind of complex, delicate global civilization we have now has only ever tried its hand at one, the calm kind. Knowing that, from the vantage point of a late-night listener drifting towards sleep, can be strangely grounding. It shrinks our sense of control but expands our sense of context. We become one chapter in a very long book, written partly in ice and rock, partly in DNA and myth. And like any good book, this one is not finished. Even now, teams are out on the Greenland ice, drilling new cores that slice more cleanly through the Younger Dryas layers, searching for clues in dust grains, volcanic ash, and tiny changes in chemistry. Others are scanning satellite data and seafloor maps for signs of buried craters or scoured channels that might support one trigger theory or another. In lakes and oceans, researchers are pulling up sediment cores, long, muddy scrolls of layered time, to see how vegetation, pollen, and microfossils responded to the sudden cold and sudden warmth. Geneticists are teasing apart the DNA of ancient skeletons and plant remains to track how human groups and ecosystems reshuffled as the climate lurched. Each new data set adds a few more pixels to the picture. Sometimes they sharpen an existing theory. Sometimes they blur it. Sometimes they reveal features nobody expected. The Younger Dryas remains, even now, a puzzle in motion. We are used to thinking of deep history as settled, like a finished mural. In reality, it is more like a tapestry that people keep carefully unpicking and reweaving as new threads come to light. The image of that abrupt cold snap, its cause, its extent, its human impact, has changed significantly over just the last few decades and will likely change again. That too is an echo in the modern world, the reminder that our understanding, like the climate itself, can shift quickly when the right threshold is crossed. Somewhere beneath the noise of our own century, the measurements, the debates, the warnings, the Younger Dryas sits as a kind of quiet baseline, a demonstration, carved in ice and stone, of how quickly the stage on which we live can be rearranged. Not to frighten, though it is sobering, more to invite a kind of humble alertness. We are children of a stable interval, telling stories under a sky that has seen far stranger years. And above the Atlantic the same winds still blow. In the deep ocean the same currents still turn. And so we circle back to that night in deep time when, as far as the ice is concerned, the world changed almost between one breath and the next. A planet easing out of the ice age, glaciers retreating, forests creeping north. Then, an interruption. A hard turn into cold. Winds shifting, currents stumbling, temperatures plunging. First in the North Atlantic, then in widening rings across the globe. 1,000-odd years of winter stitched into the end of the Pleistocene. We've watched scientists tease that story out of ice cores and lake mud, out of pollen grains and ancient shorelines. We've walked past the leading suspects, the great meltwater flood from Lake Agassiz, the possibility of fire from the sky, the slow rumble of volcanoes, the subtle pulse of the sun. We've seen how the cold touched mammoths and mastodons, how it startled early hunters, how it framed the rise of places like Göbekli Tepe, and then, just as abruptly, we watched it end. No grand curtain call, no obvious signal, simply a step back into warmth, into the Holocene, into the narrow band of climate in which coastlines steadied, ice sheets shrank to their modern remnants, and humans had the space to try agriculture, cities, writing, satellites, and late-night history videos. Yet even after all of that, the Younger Dryas refuses to sit still as a solved mystery. Each new core, each new data set nudges the balance between stories but never quite locks it in place. Maybe the meltwater mattered more than we thought. Maybe an impact did strike somewhere we haven't yet uncovered. Maybe multiple triggers overlapped in ways our models are only beginning to grasp. It is entirely possible that we will never have a single, tidy answer. There is a quiet beauty in that. Somewhere under the Greenland ice, in layers thinner than a sheet of paper, that sudden winter is still recorded as tiny shifts in trapped air and snow crystals. Somewhere on the ocean floor, in grains of sand and shells of microscopic plankton, the same story lies written again in a different script, the planet remembering itself. As you lie there, listening in the dark, it can be comforting to know that the ground beneath you holds these memories, that the calm night air above you has blown across Mammoth Steppe and glacial lakes, across worlds colder and stranger than this one, and yet here you are, breathing easily in the long afterglow of a very fortunate thaw. If you've enjoyed wandering through this piece of deep prehistory, you can gently tap like or subscribe so you don't miss the next quiet journey into the past. If you feel like sharing, you're welcome to leave a comment with where in the world you're listening from, one small modern echo of those ancient networks that once stretched between scattered bands of people under the Ice Age sky. And if your curiosity is still awake, even as your body drifts towards sleep, there's a book waiting for you, a collection of prehistoric secrets and stories told in this same soft, unhurried way. You can find it at sleepytimehistory.com. For now, though, you can let the Younger Dryas fade into the background hum of deep time. The ice, the oceans, the vanished animals and forgotten winters will still be there in the morning. The mystery will still be there too, and it will keep us wondering.